Welcome back. In this second lecture, we talk about problems and such. So, we define what a problem is. We introduce the various concepts related to problem solving in artificial intelligence. And we present ways of representing problems so that they can be solved by computers. Fine. What is a problem? There are many ways to define the word problem. First, it is anything which is required to be done. A problem is also defined as a perceived gap between the existing state and the desired state. Another definition is, it is a deviation from a norm. A problem is also the relation between human will and the reality. We can equally define problem as a state of difficulty that needs to be solved. So these are the various ways to define a problem. Now we have examples of problems. Example 1. The missionaries and cannibals problem. And this is the statement of the problem. 3 missionaries and 3 cannibals wish to cross a river using a 2-person boat. If at any time the cannibals outnumber the missionaries on either side of the river, they will eat the missionaries. How can a sequence of boat trips be performed that will get everyone to the other side of the river without any missionaries being eaten? So this is a pictorial representation of the problem. Now, questions. Question 1. What is the will? Means what is the goal? What needs to be done? Okay, question 2. What is the reality? Because in the definition of the problem, we are saying that it is the relation between human will and reality. So to define the problem, we should identify the will, the reality, and the relation between the two. We have the will, we have the reality, and we have the relation between the will and the reality. So in this problem, what is the will? What is the reality? And what is the problem? So obviously the will here is to get everybody on the other side of the river. So the 3 cannibals and the 3 missionaries on this side of the river. So that is the will. Now the reality is that there are all on this side of the river So that is the reality. The will is that they should be on this other side. Now, what is the problem? The problem there is crossing the river without any missionary being eaten by cannibals. Knowing that a two-person boat is used, it means that at any given moment a boat can carry only 2 people. So a boat can carry either 2 missionaries or 2 cannibals, or 1 missionary and 1 cannibal, or 1 person to cross from one side to another side. But at any given moment, on each side of the river, the number of missionaries should be greater than the number of cannibals. So that is the constraint. Fine. The second problem is the puzzle. So we have a 3 by 3 array containing 8 square pieces numbered 1 through 8 and 1 empty space. A piece can be moved horizontally or vertically into the empty space, in effect exchanging the positions of the piece and the empty space. So there are 4 possible moves: up, that is, move the blank space up, and we have down, left and right. The aim of the game is to make a sequence of moves that will convert the boat from the start state into the goal state. So this is the situation. This is the initial state and this is the final state. So initially the pieces are arranged in an arbitrary manner on the board. So the aim is to move the pieces such a way that they should be arranged in this manner. So there are only 4 possible moves of the empty space. So you can move the empty space horizontally or vertically. Means that it can be moved up, down, left or right. Questions. What is the will? So obviously the will is to get the board arranged in this manner. What is the reality? The reality is that the board is arranged in this manner. Now, what is the problem? The problem is to determine the sequence of moves that will convert the board from this initial state to the goal state. Fine. Now let's move to the formal description of a problem. So how do we describe a problem? How do we define a problem? A problem is defined by its elements and their relations. To provide a formal description of a problem, we need to do the following. A. Define a state space that contains all the possible configurations of the relevant objects. So that is what we should do. to define the state space. That is just the set of all possible states, all possible configurations of the object. B. Specify one or more states that describe possible situations from which the problem-solving process may start. These states are called initial state, and that is what we call the reality. For example, in the board game, this is the initial state, so that is the reality. And then in the missionaries and cannibals problem, this is the reality, this is the initial state. So all the cannibals and the missionaries are on this side of the river. So that is the initial state. Fine. C. We specify one or more states that will be acceptable situation to the problem. These states are called goal state, and that is the will. If we are in this board game, the goal state is this one. So this is the will. This is what we want to have at the end. So the board should be arranged in this manner. And then in the first problem, the will is to get all the cannibals and the missionaries on this side of the river without any missionary being eaten by cannibals. So that is the will. That is the goal state. Fine. Specify a set of rules that describe the actions or operators available. So what are the rules that describe the actions? In the board game, the actions are the moves: up, down, left, right. So these are the operators: up, down, left, right. In the missionaries and cannibals problem, the operations are the trips of the boat to cross the river from one side to another. So what is the sequence of trips that we move all the missionaries and all the cannibals from one side of the river to the other side? So those are the rules or the operators. Fine. So that is the formal description of a problem. So each time you have a problem to solve, so you make sure you define the state space, you specify the initial state, the goal state, and the rules or the operators. Fine. Example: so answer the following questions for each of the above mentioned problems. What is the state space? For the board game, for example, see, you have a series of 9 numbers, because the space can be assumed to be 0, and then 9 locations means that the state space should have a total number of 9 power 9 states. Is it like that? No, it is factorial 9. So that is the number of states. Okay. What are the initial states? So we have specified the initial states. What are the goal states? We know the goal states. What are the rows? Fine. Now, what is problem solution? So when you have a problem, you should determine the solution. So what is a solution? It is the resolution of the gap between the reality and the will. It is also the plan of action to eliminate the problem. So there is a problem. What is the solution? It is the plan of action. So what do we need to solve the problem? There can be many solutions to the same problem. A solution is also a combination of operations and objects that achieve the goals. Fine. Now, examples. Give a solution to each of the above mentioned problems. For the board game, a solution should be a sequence of moves that convert the board from the initial state to the goal state. A sequence of moves that convert the board from this initial state to the goal state. Now, for the missionaries and cannibals problem, the solution is a sequence of boat trips that get all the cannibals and missionaries on the other side of the river without any missionary being eaten by cannibals. So the solution is the sequence of trips. Fine. Now, what is problem solving? So when you have a problem, you should solve it. What is problem solving? It is the process of finding and applying a solution to a problem. So in problem solving, you find a solution to a problem and you apply that solution to that problem. For the board game, for example, we first of all determine the sequence of moves, and after that we apply that sequence of moves to convert the board from the initial state to the goal state. For the cannibals and missionaries problem, we determine the sequence of trips, and then we apply those trips to get all the missionaries and cannibals to the other side of the river. Is it okay? Fine. It is also the application of rules in combination with an appropriate control strategy to move through the problem state space until a path from an initial state, that is the reality, to the goal state, that is the win, is found. What are the rules? The rules are the operators, so we just apply the operators in combination with an appropriate strategy to move through the problem state space until a path from the initial state to a goal state is found. So in other words, problem solving is a search for a solution. It is a search for a solution. Search is fundamental to problem solving. So it is a general mechanism that can be used when a more direct method is not known. So when there is a problem and you don't have a direct method to solve it, what do? You go through the search process. You search for the solution. Search provides the framework into which more direct methods for solving subparts of a problem can be embedded. A very large number of artificial intelligence problems are formulated as search problems. So it means that problem solving can be defined as a search problem. Okay. So problem solving is a systematic search through a range of possible actions to reach some predefined goal or solution. That is what we can conclude. It is a search through a range of possible actions to reach some predefined goal or solution. Fine. Now, how do we represent the problem space or the state space so that we can search or we can find a path from the initial state to the goal state? The problem space is represented by a directed graph. What is a directed graph? It is a set of nodes, as you can see on this example. A, B, C, and D are the nodes or the vertices. Now, the nodes are linked by directed arcs. You see, this is an arc between A and B, and it is directed. You see this arrow means that on this arc we move only from A to B. You see another arc between A and C, so we can move from A to C. So we cannot follow this link to move from C to A. No. So a problem space is represented by a directed graph where nodes represent such states. So each node here is a state, and path represent the operators applied to change the state. So these directed arcs are the operators. It means that when we are in this state, in state A, there is an operator that we can apply to change from state A to state B. There is another operator that can be used to move from this state A to state C. Is it okay? Now, to simplify such algorithms, it is often convenient to logically and programmatically represent a problem space as a tree. So here we have a graph, but it can be represented as a tree like this. You see, from A we can move to B and C. So on the tree, you see, from A we can go to B, we can go to C. Now from B we go to D only. You see, from B we go to D. Now from C we can go to B, we can go to D. So that is it. From C we can go to B, we can go to D. Now from B we can go to D. So that is a tree. A tree is an acyclic connected graph, a graph with no cycle. Okay, fine. A tree usually decreases the complexity of a search at a cost. The cost is due to duplicating some nodes. In this way, you see, we have duplicated B and D. B appears 2 times, D appears 3 times, so that is not duplication. So that is the cost. Fine. Example, give the problem space representation of each of the above mentioned problems. Okay, for the missionaries and cannibals problem. Okay, this is the problem space representation using a graph. So at the beginning, you see, we have 3 missionaries and 3 cannibals, and then we have the boat. The boat has 2 positions, so it can be on the first side represented by 0, or on the other side represented by 1. And then this is the number of missionaries left, the number of cannibals left. Okay, since we have a 2-person boat, so you can carry only 2 persons, So in the first trip we can carry 2 cannibals. If we carry 2 cannibals, now there are 3 missionaries left and 1 cannibal left, and the boat is on the other side of the river. Or we can carry 1 missionary and 1 cannibal. At that moment there are 2 missionaries left and 2 cannibals left, and the boat is on the other side of the river. So these are the 2 alternatives, because we cannot, in the first trip we cannot carry 2 missionaries, because if we do it, there will be 1 missionary left and he will be eaten. That missionary will be eaten by the 3 cannibals. So these are the 2 options. So either we carry 2 cannibals or we carry 1 missionary and 1 cannibal in the first trip. And in other situations, you see, in this situation, this is the new state, and this is the new state. Now from here, what do? We can bring back 1 missionary. At the moment there are 3 missionaries left and 2 cannibals. You see, here the number of missionaries is greater than the number of cannibals. So the cannibals cannot eat the missionary. Now on the other side of the river we have 1 cannibal and 0 missionary. So no missionary can be eaten by cannibals. Now if in the first trip we carry but 2 cannibals, at that moment we can bring back 1 cannibal, so that on the first side we have 3 missionaries and 2 cannibals. So in either situation, you see, you have 1 cannibal on the other side of the river. So 1 has crossed. Now we have 3 missionaries and 2 cannibals. Now we can now carry the 2 cannibals in the second trip, or that is the third trip, to cross from the first river to, or from the first side to the second side. Now there are 3 missionaries left. Now in the fourth trip, and then you see the position of the boat on the other side. Now we bring back 1 cannibal. Now we have 2 cannibals on the other side now, 1 on the first side and 3 missionaries. At this moment, you see, on the next trip we can carry 2 missionaries. Fine. And at that moment 1 missionary and 1 cannibal left. Okay. We can bring back 1 missionary and 1 cannibal. the next strip we carry 2 missionaries. At that moment you have succeeded to carry all the missionaries from one side to another. Now the boat can go back empty to bring the 2 cannibals. That is cannibal. So that is the problem space representation of this problem. Now let's move to the second problem, the board game. Okay, this is the initial state. From the initial state you see from this state there are 3 possible situations. We can move left, right, or up. So so you see we have this situation. If we move up, so these are the 3 situations. If we have left and right, okay, if you move up it is going to be like this. So this 6 is going to go down like this, up, and then left. So the empty space you move to the left. So it means that this 7 should move to, so that is left, and then right. So okay, so from initial state, when we apply the operators, you see these are the new states that we obtain. From if we take this state, for example, from here we can, there are 4 operators that can be applied. So can be up, down, left, right. So if we apply the operators, so we can have something like this. So from this state we can go like that. Like that. And then from this one we can have two. We can apply two operators from there too. Okay, but let's follow this this one. So if this right, left, up, down. So these are the operators. So up, we are going to have this new state 3. Down, if we go down, so 6, 6, 6, and then right, so these 2, and then left. If we move to the left, this 8 is going to move like this. 8. Okay. So that is the problem space representation by a graph. And then in this particular situation, this is a tree. Is it okay? So that is it. Fine. Now to conclude this section, a problem can be represented as a state space search problem. A state space represents a problem in terms of states and operators that change state. A state space consists of a representation of the state the system can be in. For example, in a board game, the board represents the current state of the game. a set of operators that can change one state into another state. For example, in the board game, the operators are the moves up, down, left, and right. An initial state, a set of final states. And we need a search control strategy to solve the problem. Thank you for your kind attention.